Hello everyone, and welcome to module 4, I think it's 4. Yes, module 4. In this module we will be covering chapter 11. I'll try my best to cover the entire chapter in this video lecture. If I can't, I will split it into 2 videos, but hopefully I will. Anyway, the subject of the chapter this week is impulse and momentum. What is impulse? When we say impulse, it means you have a force that is imparted on an object in a very short time. Okay? It's different from, let's say there is a cart in the grocery store, and I hold the cart and I push the cart across the aisle. That's not impulse. That's work, right? What is work? Work, you have a force exerted on a body, and as a result of that, the body moves a distance x or d. Okay, that will be work. Okay, work equals Fd. We talked about that before. Impulse, however, is, let's say there is a soccer ball and I kick it. Okay, that's impulse. Why? Because the force here, the time of contact here is extremely small. It's a fraction of a second. So the force exerted on the object was very, very short, small, and that's impulse. For example, you're playing baseball and you have the baseball bat, and then the ball comes to you and you hit the ball with the bat. Well, the time of contact of the ball with the bat is a fraction of a second. Let's say something like in the order of a tenth of a second, and that's impulse. So impulse is a force exerted on an object in a very, very, very short time. Okay, playing ping pong, tennis, ping pong, or anything like that. Okay, that's what impulse is. Momentum, however, let me go back to this. Okay, momentum. So let me talk about impulse. Impulse, force imparted or exerted on an object for a very short time. Think of the word kick, for example, okay? Hit and so on, okay? All right, momentum, however, momentum is the symbol for momentum is P, okay? I'll come back to that, but it's P. P is equal to the product of the mass times the velocity. This is called momentum, MV. Okay? The best way to think about it, momentum is like the collisional power of an object. Okay? This is not the formal definition of it, but that's how you should picture it. The collisional, if this is a word, the collisional power of an object. Let me ask you this question. Let's say there is a wall. Okay, imagine there is a brick wall here. Okay? Okay, and you have, let's say there are 2 people here. One person has a gun, and in the gun there is a bullet, let's say, say 22 millimeter bullet, small bullet, say the size of a cigarette filter. Okay, and then another person, he has a big boulder. Okay, so the person here, the guy with the bullet, he pulls the trigger, the bullet leaves the barrel, and it hits the wall here. The guy with the big boulder, he lifts the boulder above his head and he throws it as hard as possible, say here. Which one do you think will make more damage? That's a good question. Which one do you think will make more damage to the wall? I usually ask this question in class, and we are almost 100 students. If you are in class, I'm very sure there will be something like, the class will be something like 50-50% split between. Somebody will say the boulder, somebody will say the bullet, and maybe some other people will say I don't know. Why they're confused. So why the split here? Because everybody's thinking of two things. Well, the people who think of the bullet will think, well, the bullet is going really fast. The velocity is very large, even though the mass is really small. I mean, the bullet has a very, very small mass compared to the mass of the boulder, but it is really fast. I'm talking here, the speed of the bullet is something like Mach 1 or Mach 2, twice the speed of sound, really fast. The boulder, on the other hand, it's very big, very massive, right? But it has a very small velocity. I mean, it's just me throwing it, so that's maybe, it couldn't be more than 3-4 miles an hour. Very, very small, right? So the damage here is caused by the mass. Well, now imagine a boulder going at the speed of a bullet. Now that would be extremely damaging, something like the artillery shell. You see what I'm saying? So here we have this fatal combination of velocity and mass. Those two together will give you that collisional power that I just referred to. You see what I'm saying? So momentum, when you think of the word momentum, the first thing that should come to your mind is the power of that collision. For example, a semi-truck going 55 miles an hour versus a Honda Civic going 55 miles an hour. Which one will make more damage to, let's say, God forbid, both of them collide with a concrete wall or something? Which one will make more damage? And so on, okay? So the momentum, in that sense, it has to do with the product of the mass and the velocity. It has to do with collision, okay? All right. So how the two are related, how impulse and momentum are related. Okay. Let me just give you some mathematics here, and then we'll talk more about it. So we know that F equals ma for Newton's second law. Now, if I have ma, and of course that will be F dv over dt, right? The acceleration is the derivative of the velocity with respect to time. And this is equal to the force. If I keep it in that. In this case, the force is a function of time. Let's assume, but sometimes the force is a function of position, just like we did with the case for work. Remember we said work is equal to F dx. Well, what is this F? F here is a function of position, okay? This kind of force here is a function of time because it happens, remember we defined the impulse to be imparted on an object in a very short time. So this force here by its own nature is a function of time. You got that? It's kind of a different force. Okay. Now if I move this dt here, so I'm going to have m dv equals f of t dt. Okay? Integrate both sides like that, where this one from some initial velocities to some later velocity v, okay? And this one is from, let me call it v prime for now, okay? So some initial velocity v naught to v prime. And then here we are integrating with respect to time, some t1 to t2 maybe, or t prime, whatever, okay? So when I do that, what do I get? Well, this gives me mv from v naught to v prime equals to this integral. I can't integrate it really until I know the nature of this, the force. Oops, sorry. dt, okay? This gives me the left-hand side, gives me mv prime minus mv naught equals the integral. Okay? Okay. Take well, let's just see what that is. Okay, so what does that mean? What does this left-hand side means? Well, this, remember we said that momentum is equal to mv. So this one is basically p prime minus p naught. In other words, the final momentum minus the initial momentum is equal to this integral. Well, what is this integral? We define this integral to be what we call the impulse. So the impulse really what is the impulse? The impulse is really the integration of the force dt. If the force, provided that the force is a function of time or a constant. Okay, that's basically what the impulse is. Now, also, as you know from your calculus courses, this integral, if I have a function, if this is the t-axis and this is the f of t-axis, so I have something like this. So let's say I got this. Okay, this is the function f of t. So the integral from point here to point here, not necessarily 0, maybe something else, from a to b, okay, it's basically the area under the curve. You see what I'm saying? So this one is nothing but the area under the curve. Of the function f of t. That's what I'm saying. Okay? I'll give you an example and show you what that means, but that's basically what it is. Now, what is this now? Well, this is also impulse because they are both impulse, because they are both equal to each other, okay? But that's the difference in momentum, correct? Okay? So this is the difference in momentum. Let me explain to you what that means, what this equation means. Let's say we are playing baseball, okay? Here is the bat. I'm going to go this way. How do I go? Let's start here. Here's the bat, okay? Here's the ball coming towards me, okay? The ball initially at some velocity v0, okay? I'm holding the bat. Let's ignore the speed of the bat. Let's assume that the bat's speed is not moving, okay? So the ball is coming toward the bat. This is what I call BC, before collision, okay? Then I have what I call DC, during collision. What happened? The ball touches the bat, and now it is in contact with the ball, with the bat, momentarily for a fraction of a second, something like that. Okay? I mean, this, you can't even see it with your own eyes because it happens so fast. You just hear sound of the collision. So for a very short time, you have the bat is in contact with the ball. Got it? And then we have AC. AC, basically you have the bat, and now the ball is moving away from it with some new velocity v0. Got it so far? Okay. If I want to ask the question, let me just concentrate on BC and AC. Okay. Here, if I ask you the question, what is the momentum here? P. Since this is P0, I'm going to call it V0, I'm going to call it P0. So that's equal to what? Well, it is the mass of the ball. The mass of the ball is m, right? And we said that the momentum is mv, so that's going to be mv0. Is that okay? But keep in mind, since the velocity is a vector quantity, this means the momentum is also a vector quantity, which means direction is important. Here we have the velocity moving to the left, so we have to have a minus sign there. So far, so good? Okay. Now, let's talk about AC here. I have here P prime equals to MV. MV prime, that is, and it's positive because it's moving to the right. Yes? Okay. We said that the impulse, and by the way, your book calls impulse J, okay? Let me go back to the formula. So this is, we can say this is equal to J, or this one is equal to the impulse J, okay? Your book calls it J, and I've seen it especially in engineering books, they call it J for impulse. Anyway, okay. So in this case, the impulse J, remember, it is equal to what? If you go back, let me write down exactly what I've written here. It's equal to this, mv prime minus mv0. So basically the difference between the final minus the initial. What is the final here? Well, the final is this one, right? So this is p prime minus p initial. watch what will happen here. Let me plug him in. So I have here mv prime minus mv naught. So I have mv prime plus v naught. You see that? So that is the impulse. Even though it says the difference, in reality, really you're adding them up because these are vectors. You got that? Okay. So that's one way to define impulse. So I can calculate the impulse with that. Now, also, I can define it, what does it say? If you go back here, we can also define it as the integral. Okay, the integration of the force. Okay. Now, most of the time for this level of physics, we will always assume that the integral here is constant. Okay. So that means you just kick it out of the integral. But keep in mind, it is always the area under the curve. Okay. So it is always the area under the curve. Here. When you integrate it, that is. Okay. So here, basically, I'm going to look at DC, which is during collision. What's going on during collision? Well, there is a force here. See what I'm saying? There is a force that is imparted on the baseball due to the ball. And that force, this impulse that we define as impulse, is equal to, in its simplest form, is F delta T. Okay? Now, if F is not a constant, so we can integrate it, okay? So we could just say it's that. But it's also area under the curve if I know an expression for the force, okay? So now I have the following formulation. So this is also impulse. And this is impulse. So therefore, mv prime plus v naught, which is this, is equal to F delta T. So that would be one way to define impulse, okay, which is basically similar to what we have, what I have just showed you above. Okay, let me do an example and show you how this works. And I will start with example. By the way, this is you can go back to your book, equation 11.6. He talks about it. Oh, I have the book here. Let me show it to you. Page. So here we go. As you can see here, here is the curve. Here is the force axis, and this is the time axis. So the area under the curve is there. The duration of the collision. Contact begins here, and contact ends there, and so on. Okay, and then he does what I have done for you right now, and then he defines the momentum. And then, there we go, we have delta P is that, and then there we go, that's the equation we're referring to. The impulse is the integral of the force dt, okay? So it's basically, there we go, another equation for it, delta P equals J. He put X here because it's just one dimension. That's cool, that's fine. Analogy for energy principle. All right, let me give you an example. I want to do this example right here. The one that you see, example 11.1, okay? The problem says, it says 150-gram baseball is thrown with a speed of 20. It is hit straight back toward the pitcher at a speed of 40, okay? The interaction force between the ball and the bat are shown in the figure. Excuse me. So we have, this is the figure that represents the force that was imparted on the ball. You see what I'm saying? His question is, what maximum force does excuse me, let me repeat it again. What maximum force, F sub max, does the bat exert on the ball? Basically, see that F max right here? He wants to know this peak right there, that peak value, what is it? And he said, what is the average force of the bat on the ball? Now, the average in general for any function, even basically from calculus, is the area under the curve. That's the average value, okay? Now, the maximum value is something like that, okay, where the peak of it, well, I'll come back to it. I'll show you what that means, okay? All right, so how do we do this problem? Let me go back to here. let's write down what's given to us. So we have here example 11.1. So we have the mass of the ball is 150 gram. Okay. The initial velocity is 20 meters per second. And the final velocity after it was hit is 40 meters per second, right? And the graphs look something like like that. Try as much as I can to make it look symmetric. Like this. The width of it, let me go back to the picture. Look at the picture. It says the width of it is 3 milliseconds. You see that? So it's 3 milliseconds, and then the height is F max is not given to us. This is what we're supposed to find. Okay? So 3 milliseconds here. And this is F max. This is the force function, and that's the time axis. You got that? Okay. So we know that delta P is equal to the impulse. Remember that? Remember the formula? All right. So if I want to find the impulse, which is basically the mass, and you remember you end up adding them together because they go in opposite direction. So if I'm going to show you a picture of that, it would look something like, here is the bat, you know, this is BC, okay? And let's say the ball initially is going like this with 20 meters per second. And then AC, here's the bat, and excuse me, and the ball is going in this direction, 40 meters per second. You see what I'm saying? So if I apply this picture on what we are doing, it's going to be something like that. Minus 20, minus 40, correct? And that will give me, the mass, of course, is 0.15 kilogram, right there. Time minus 60. Remember, the minus here is just a direction. Okay, remember, momentum is a vector quantity. So that will give me minus 9 kilogram meter per second. This is the unit of the momentum here. Momentum is mv, right? So in terms of unit, that's kilogram meter per second. Keep that in mind, okay? That's the unit of it. Okay, so there we go. So we have the momentum. Now, let me get the area under the curve, which is basically, I'm looking at this triangle right here. So I want to get the area under the curve. Okay, so what is the area under the curve? Is basically the average force. Okay, so the area under the curve, I'm sorry, the area under the curve is the impulse, right? Okay, remember we said impulse is F dt from T1 to T2, and that's the area under the curve. Okay, I wanted to say the area under the curve is the impulse J, which basically should equal, remember, this is also the impulse J. You get that? Okay. So let me get the area under the curve. And that would be 1/2. So area, should I call it, let me call it J anyway. And that's equal to, you know, a triangle here. We have a triangle, so it's just going to be 1/2 the base time, base times the height, right? Now here is the trick. Watch this. What is the height? Well, the height is basically F max. See that? The height is F max. So basically, J here is 1/2. The base is 3 milliseconds right there. 3 times 10 to the negative 3. And the height is F max. And that's equal to J. Well, what is J? I just got it. J is equal to this, 9. Let's just put it 9 here, because the minus here just tells a direction. So, so I can just solve for F max. You get that? You see the trick? See how you get F max? You don't need any calculus or anything fancy. So in this case, so I have 9 equals 1/2. Let me just write it down again. 3 times 10 to the third times F max that will give me 1.5 times 10 to the negative third F max, and this is 9, and therefore F max, which he's asking for it, is equal to 9 divided by 1.5 times 10 to the negative third, and then we can calculate that. Let me calculate it. You know what? Hold on. I think I made a mistake. When I multiply, what is it? I'm sorry. When I multiply those two together, do I get 9? Is that right? Yeah. Actually, we get 9. Sorry. Yeah. Let me do it again. 60 times 0.15. Yep, we got 9. This is fine. There's no problem with that. I'm just checking if there is any. Oh, okay, I got it. Okay, you know why? Because in my notes, the width is 6 millisecond, not 3. So, okay, this one is 3. That's why I'm getting a discrepancy. But anyway, this is okay. We are just following the book. So we get that, and then let's calculate this. So that's going to be 9 divided by 1.5, negative 3. Answer, oops, 9, I'm sorry, divided by 1.5, negative 3. And the answer would be, if I do it correctly, I got 6,000, I hope I did, Newton. There we go. So F max here is equal to 6,000 Newton. Okay? And if I want to get the F average, how do I find the F average? Well, we know that delta P is equal to F average delta T. The usual formula, that simple formula. So F average is delta P over delta T. Delta P, we got it, which is basically the impulse, right? It's equal to 9. Do I need to show it to you? Sure. It's right here. Here it is, delta P. It's equal to 9. Again, the minus sign here, it doesn't contribute much to what we're doing. Divided by delta T. Delta T is basically what we got here, which is here right there. That's 3 milli. So divided by 3 times 10 to the negative 3. So that will give us 9 divided by 3, negative 3, and that will be equal to 3,000. Do you know what's another way to get the F average from calculus? How to get the F average. Another way of doing it, it is generally acceptable to say any value, any average value is always equal to half the max. In general, just keep that rule in mind. If you're in a hurry, you want to calculate the average, if you know the max, just divide by 2. Okay? Generally, this is in general. It's not how to do with this problem. So our max, well, we get the max to be 6,000. So therefore, F average will be 6,000 divided by 2. And that will be 3,000. There it is right there. Got it? So that would be one way to do it, okay? But technically, we should do it that way, okay? Good. All right. That's all I wanted to talk about as far as impulse is concerned. Now I want to talk about collision, conservation of momentum. Conservation of momentum. Okay. The thing about momentum, MTM, let's do it. The thing about momentum, we last time we talked about conservation of energy, and we said that energy is equal to kinetic plus potential, U, right? Well, we have another conservation law, and that is the conservation of momentum. Let me explain it to you. What does that mean? What's the meaning of conservation? And that's, again, it's a universal law. It's part of nature, okay? The natural law. Let's say, for example, there are 2 balls. Two balls are rolling toward each other. They're about to collide with each other. Ball 2, ball 1. They're going toward each other like that. The ball 1 has an initial velocity v01. Ball 2 has initial velocity v02. Mass of ball 1, m1. Mass of ball 2, m2. Got it so far? This is all BC. Okay, before collision. After collision, they collide and then they rebound. So let's assume ball 2 is moving with this direction, v2 prime, and then ball 1 is v1 prime. Okay, of course nothing have changed about their masses. Okay, so let's say they're a billiard ball or something. All right, fine. That's AC. Okay, now let's assume further that I want to get the momentums of ball 1 and ball 2 before collision. Okay, so what is the momentum of ball 1 and ball 2? Oh, sorry, I want to get the momentum of ball 1 and ball 2 and add them up together. I want to get the sum of the momenta. Got it? Basically, I want to get P01 plus P02. You see what I'm saying? And I also want to get the sum of the momenta, P prime 1 plus P prime 2. Got it so far? So what is P not 1? Well, P, remember, momentum is mv. So that's going to be m1 v naught 1. Right? What about P naught 2? Well, it is m2 v naught 2, but because it's moving to the left, it's going to be negative. So that's going to be minus m2 v naught 2. Hold on, let me get a drink of water. Got it so far, guys? Okay, so we have that basically the sum of the momenta. Remember, these are vectors, so we have to take care of the minus and plus sign. So there we go. This is the sum of the momenta, BC. Sum of momentum, MTM, BC, before collision. Now let's do the sum of the momenta, AC. Well, it's going to be, pay attention to the direction, the signs. So P1 prime is going to be negative, so that's going to be minus M1 V1 prime, plus for P2 is to the right, so that's going to be M2 V2 prime. Okay? So far so good? Here is the question. How those two sums, before and after, are related? It turned out they will always be equal. In other words, this is a natural law. The sum of the momenta before collision is equal to the sum of the momenta after collision. Very, very important law. Got it? Okay. Let me give you an example. Well, before I give you an example, I'm going to tell you about two types of collisions. Let me just go on about this and then we'll do example. Two types of collisions. One is called elastic collision and the other is inelastic collision. And the other one is inelastic. Okay, an elastic collision, okay, it means the two colliding bodies don't stick together, okay? So two colliding bodies do not stick together AC after collision. Okay? That's one aspect of it. But really, this is not the true aspect. The most important thing about elastic collision is that the kinetic energy is conserved. I didn't say energy. I said kinetic energy. Okay, I'll come back to it in a sec. Okay, inelastic collision means the two colliding bodies stick together. And the kinetic energy, Ke, is not conserved. The second statement for both is more important, okay? What does that mean? Let me go back to the scenario that we had here. We have two colliding balls here, and then the after and before collision and so on, okay? And then we were able to find the sum of the momenta before and after, and it turned out that the sum of the momenta before is equal to the sum of the momentum after. Great, okay? Because the two bodies here, the two balls, don't stick together, and it is an elastic collision, then the kinetic energy before and after are equal, the sum of the kinetic. Let me show you what that means. So if you take this picture, please, you can pause the video and draw this picture, because I'm going to move to I'm going to go downwards, so you're not going to be able to see this picture. So you may want to pause the video and draw it first. So now, if I go back, oops, there we go. If I want to get the sum of the momenta before and after, sum of the kinetic energy, BC and AC. So what will happen? Let's look at BC here. So I have 1/2 M1 V01 squared plus 1/2 M2 V02 squared. This is the sum of the kinetic energy before collision, okay? Now, if I do it after the collision, it's going to be the same thing. It's going to be 1/2 M1 V prime squared, V1 prime squared, plus 1/2 M2 V prime 2 squared. You got that? The sign doesn't matter because you're squaring it. You see what I'm saying? If it is elastic, then those two are equal. So equal if elastic. Okay? If inelastic, then the two kinetic energies here are not equal. Okay? So I'll come back to this inelastic in a sec. So what does that mean? It means the sum of the kinetic energy before collision is equal to the sum of the kinetic energy after collision. So now we have two conditions. The first condition is the sum of the momenta before and after are equal, and the sum of the kinetic energy before and after are equal. So this sum of the momenta before and after are equal. If those two conditions are satisfied, that's elastic. Okay? But if only the second condition is satisfied, in other words, if it is sum of the kinetic energy before does not equal to the sum of the kinetic energy after, but the sum of the momentum before equal to the sum of the momentum after, that's inelastic. You got that, guys? Let me go back. It seems like it was, oops, I have to sign in again. I'll just do it when I need it. Okay? You got it? All right. Let me give you an example. I'll show you how this works. I hope you're taking notes. And by the way, I've gotten a couple of emails from you saying that you're having difficulty doing the homework problem, or you're not doing well on the quiz. You are more than happy. I'm trying to provide for you as much as I can. I am providing that Ask the Professor forum and the discussion forum. If you're working on the homework and you get stuck on one problem, just tell me about it. Just post it. Say, hey, Dr. Raja, problem number 57. I can't do it. Can you help me out with it? I'll be more than happy. I can just work it out and then take a picture of it and just scan it right there so you can see it. I have no problem with that. So you feel free to ask me about any problem in the book that you're stuck on. Okay? I'm here to help you. So it's unfortunate that we're not talking together in person. We're doing this lousy stuff. But, that's just the way it is. You know what I mean? Okay. Let's do this example. So you have two gliders, M1 is equal to 200 gram, and M2 is equal to 400 gram. And glider number 1 is moving with a speed of 3 meters per second. Okay, they stick together after collision. So you get one glider here. Here it is. Glider 1 moving in this direction. Glider 2 moving in the opposite direction. Okay, they are both on the same, air track or whatever it is. Okay, and then after the collision, they both stick together and they become only one mass. Okay, and they move with one common velocity, big V. Okay, so this is the common velocity for them. Okay, he's asking for, we have the velocity of glider 2 before is equal to, or is it not given to us? Sorry. Oh, sorry, this is not given to us. Okay, so V02 is not given to us. V01 is given to us. It's 3 meters per second. This one is unknown, but the common velocity is given to us, and it's equal to 0.4. Okay. He said, what is the original velocity? What is V02? This one. Okay. So first of all, let me show you how do you get the equation of the momentum for an inelastic collision. Now, like I said, inelastic collision, they stick together after collision. So basically, here's the general equation. Okay, before I do this problem, just general equation. Let's assume that we have, here's glider 1, here's glider 2. Let's say they're moving in opposite direction, like that. V01, V02. Let's say after collision, they both move in this fashion. Doesn't matter which direction. Let's say this way. This is BC here, and that's AC. Okay. So basically, the sum of the momentum in this case is going to be what? M1 V01 minus M2 V02 equals to, now what happened after the collision? They stuck together. Now it's one mass, M1 plus M2, multiply what we call the common velocity, which is this velocity V is common to both of them after the collision. Okay, this is basically the formula for any inelastic collision. That's how it looks like. Now let's apply those ideas to our problem. But look at the picture here. It looks a little bit different. The only difference is that the big V here is moving in the opposite direction. So anyway, let's apply it. So for our case, so I have M1 V01 minus M2 V02 equals minus, correct, M1 plus M2 big V. Why is minus? Because it's moving in the opposite direction, not like this direction here. Okay? And all I need to do is just plug in all the numbers that I have, and I solve for V02, and I'm done, really. It's a simple problem. So here I have, what do we have here? So M1 is 200, let's see. You know what? We can put 200 grams here because they're going to cancel out. All right, you see what I'm saying? So we can just do that because that will cancel out anyway. The gram units on both sides. So that's going to be 200 times 3 minus 400 times V02 equals to minus 200 plus 400 big V. I forgot V is given to us. It is 0.4, correct? You remember the grams on both sides are going to cancel. So we have here 600 minus 400 V02 equals to minus 600. Is that right? Yes. Minus 600 times 0.4. And that's equal to, let me use my calculator. 0.4 times 600, answer 240. So that's negative 240. And then you just work out the algebra, and therefore V02 is equal to minus 240 minus 600 over minus 400. Is that right? Did I do it right? Hope I did. minus, you put that, yeah, it becomes a lot of minuses here. So we have 840 minus over 400. So we have 840 divided by 400. I'm using my calculator again. It's 2.1 with a minus here, so that's a plus 2.1. Should be minus or plus? Should be minus, right? If we do it correctly, according to the picture here, it should be in the minus, and that minus should be there. Oh, I know what happens. I already took care of the minus right here. Okay, that's why we didn't get the minus. You see what I'm saying? I already took care of it. Had I just said I don't know the direction of V2 and I kept it plus, I would have gotten the minus. You see what I'm saying? So I already knew beforehand it's a minus right there. So anyway, there we go, meter per second. I am looking at my notes here. Let me make sure I'm doing it correctly. I mean, unfortunately, no one around me to say, hey, you did a mistake there. It's in direction in the minus direction, so that's going to be corrected to the minus. I put that minus in there. Plus, and then I would have minus 400 minus, and then I would have minus 600 minus 400 there, and then I would move the 600 to the other side. It's going to be minus 600 over minus 400, and I think I did it all right. You let me know. I think I did okay. Like I said, just because I put that minus there, that's why I did that minus sign didn't show up here. Okay, let's assume this is correct. If not, please let me know. Okay. Here is a tough one. Okay, a little bit tougher. Not very tough, but it's kind of nice problem. Again, this is from my notes. So here you have two cars collide and stick together. And skid 3 meters until until they stop. Okay. Assume the coefficient of friction on the street is 0.8, and given, here's the following, what's given to us. V01 for car 1 is equal to 5 meters per second, and the mass of car 1 is equal to 2,000 kilogram. The mass of car 2 is equal to 1,000 kilogram. Okay, and they skid, and we want to find what is the velocity of car 2 before collision. Got it? Let me draw a picture and show you how it looks like, at least a picture in my notes here. So here is the car 1. That's car 1. And this is car 2 here. Okay. That's car, I'm sorry, this is car 1, this is car 2. And this is V02. This is V0. Look at the direction here, guys. Okay. So this is M1. This is M2. So both are moving in the same direction, except that it apparently V02 car 2 is going faster. That's why it collided with it. So after the collision, what happened to them is that they collide. Here they are. How do I draw two collide cars? There's another one here. There we go. They both collided together and they move with one common velocity, big V. Okay? And they skid. They have a skid mark until they stop here. And that skid mark is 3 meters. This is skid mark. Got it? Okay. He's asking for what is V02. Got it? You understand the problem? Okay. So, obviously, this is an example of inelastic collision because the cars stick together. So I'm just going to use the rule for inelastic collision. I have this picture, so I'm going to draw everything. All my signs are going to be dependent on this picture. Okay. So let's do it. So I have here M2 V02 plus M1 V01 equals to M1 plus M2 times big V. Now this V, what is this V? Well, V here is at the moment of collision, right? I mean, remember, it stopped here. It stopped right here, which means that here the velocity is big V, this one, and then it started decelerating until it stopped here. So that's the final is 0. You see what I'm saying? So this big V here is the moment of collision. At the moment. It makes sense, everyone? It cannot be constant. If it's constant, there is the skid mark will keep going. You know what I mean? So it's decelerating here. So one way to draw this picture of those two cars, I can draw it like that. The moment they collided together, it skid for a distance 3 meters, okay, while you have a friction force on them like that. Stopped right there. Got it? So here I have, okay, I get this equation right here, the momentum equation. I don't know the big V really, the initial, that moment of collision, I don't know it. And I don't know V02. But let me appeal to dynamics. Let me appeal to this, the equation here of the force, the friction force. So that's the only force on it until it stopped here. Right? So we can say that it is F equals M, remember this is M1 plus M2 plus M2 that, right? I mean, I can put a minus sign there as an opposite, but the minus is not important really. I'm merely interested in this acceleration. Okay. So, what is F here? Well, F is mu n equals M1 plus M2 A with a minus. And then N here is what? M is the mg, right? So this is N right there. This is M1 plus M2G. You see what I'm saying? So that's minus mu M1 plus M2G equals M1 plus M2A. Those cancel out. So therefore, the acceleration, or deceleration rather, is equal to minus mu G. So that's minus 0.8 times 9.8. You got that? Let me calculate that. So I have 9.8 times 0.8 equals 7.84. So the deceleration rate is negative 7.84 meter per second squared. Okay? All right, great. Well, what do I need it for? What do I do with it? You can pause the video and think about it if you want to, okay? You can pause the video and think about it. But here's what I need it for. I'm going to give you the answer now. Go back to this diagram right here. I can use kinematics to find the velocity here, which is basically the big V. See, I have the acceleration, right? A deceleration rather, and I have the distance, and I know the final velocity is 0. Well, my gosh, I can find the initial velocity, which is basically what? Big V. Do you see the trick? Okay, so I can use second kinematic, which is this one. V squared equals V naught squared plus 2ax, where V naught here really is big V. Let's put it in our notation. And this is, of course, the final velocity, which is 0. So that's 0 equals big V squared plus 2ax. X is the skid, right? So therefore, v, big V, is equal to the square root of negative 2ax. So we have negative 2a is negative 7.84. You see what I'm saying? And the skid mark is equal to 3. And from there, this is, doesn't look good. There we go. Negative 2, okay? And then I can calculate that. Minus minus will go plus, and I can calculate that, and I got 6.9 meter per second. Aha. So basically, the moment, go back to the cars, the moment the two cars collide right there, okay, this velocity is this number, the one we have just gotten. Got it? So now what's left? Well, the rest is easy. I take that number and I plug it into here to solve for V naught. Let me use another color. How about red? How about pink? I'm sure somebody will appreciate pink. Okay. So there we go. We're going to use it. We're going to plug it in there, and then we're going to find V naught 2. That's basically what he's asking us to do, right? So you back to this equation. So may I call it 1? So plug back into 1, and then when we plug it in, so I'm going to have in this case, go back to 1 right there. Please write it down, and I'm not going to show it anymore. So that's going to be something like 2,000 times 5 plus 1,000 V naught 2 equals to 3,000, you know, when you add them up together, times 6.9, right? And then you just solve for V naught 2. V naught 2 is equal to 11 meter per second. When you work it out, it's that. Okay? You got that, guys? Okay. Great. Okay, one more. We have been talking for almost an hour. I think I can do another 20 minutes or so. Here is a problem that is not, I would like to do at least 2 problems from the homework, or one particular one from the homework that is hard to some people. Number 25, at least this one. And like I said, you work on the homework, you get stuck on one of them, you know, post it. Post it and ask the professor or discussion forum, and I'll help you out with it. So, all right? Okay. I mean, I would rather have you work on it rather than me giving you the solution to that. That's the point. And I understand you are at home with no teacher, nobody's looking over your shoulder, you know, no office hours, none of that. I understand all that. I really do, and I sympathize, but just the way it is. All right. Here's another topic in this chapter. It's called explosions. And when we say explosion here, we mean you're starting with 0 momentum, and out of a sudden you have a huge momentum. An example of that would be when you shoot a bullet from a rifle. Okay, so here is a rifle barrel, and here is the rifle right there, and there is the bullet lodged in here, right? And then you pull the trigger, right? And what happened is that the rifle will jerk backward with some velocity, let's call it v, okay? And the bullet is going to shoot forward with some velocity, big V, okay? Let's assume you know the mass of the bullet and you know the mass of the rifle. Let's make the mass of the rifle big M, and the mass of the bullet is small m. But the velocity of the bullet is big V, and the velocity of the rifle is small v. So how would I solve that? Well, basically, explosion means the momentum of both particles, rifle and bullet, are equal. Why? Well, we're starting with 0 momentum. I mean, right here, if you look at this rifle right there, so what is the momentum here? Well, 0. There's no momentum. You see what I'm saying? The bullet is not moving. and the rifle is not moving. Here, on the other hand, well, what is that? Well, let's see. Let's work out the momentum here. Remember, the rifle has a big M, and the bullet has small m, right? So it's going to be minus big M, small v, plus for the bullet, small m, big V, equals, conservation of momentum equals, this is BC. This is AC. See what I'm saying? I mean, before explosion, BE maybe, and after explosion. So now I move one of them to the other side, so it becomes MV equals M big V. Okay? And that's really the equation of an explosion, is that the two momenta are equal. Okay? So, for example, if I tell you that, let's say here's an example, which is related to this bullet rifle thing right there. Let's say that the mass of the bullet is 10 grams, and the mass of the big M here, the mass of the rifle is 3 kilograms. Okay, and let's say the velocity of the bullet is 500 meters per second. Remember, the speed of sound is 340, I think. So that's not exactly double, but a third more. And now you want to know the velocity of how much the rifle will jerk. Okay, so that's a rifle. Okay, so all you need to do is you just equate them with this, use this formula. The mass of the rifle is 3 kilograms times the velocity of the rifle, which we're looking for, equal to the mass of the rifle, excuse me, the bullet, 10 times 10 to the negative 3 kilograms, times the velocity, 500 meters per second. And then you work it out. So therefore, the velocity in this case, it will give you 1.67 meters per second, I think. I'm copying this answer from my notes. And there we go. You get the velocity of when the rifle hits back, when it hits back on your shoulder or something, it hits back with this kind of velocity. Okay? All right. I'm going to do at least 2 more problems. There is an example, example 11.5. I don't know if I can get it quickly here. 11.5 in the textbook. Section 11.5, page 273, section 3. Let me just go back one more. There we go. One more. 11.4. Please read 11.4. 11.5, right there. Okay. This is called a ballistic pendulum. Okay. A ballistic pendulum is an old-fashioned way of calculating or measuring what is the speed of a bullet. Okay. I've actually done that. I witnessed that back in the 80s when I took this course with our professor. I'm talking 1982, long time ago, back in those days. And professor, believe it or not, he had a gun in the lab, a real gun. I'm talking real gun. I think it was a smaller gun, maybe 22 millimeter. And he had a ballistic pendulum, and he actually had us all go behind him, and he was in front, and he shot the bullet right in the lab on a piece of wood, the ballistic pendulum, to measure the speed of that bullet. We actually did that in class. Of course, you could never do that here, not nowadays, right? Anyway, so let me tell you the story of it, how a ballistic pendulum looks like. Oops, I'm not going to do there we go. Okay. So I don't need to read all that. I'll just tell you the story. Well, let's read very quickly. Sorry. It said a 10-gram bullet is fired on 1,200-gram wood block, which is about 1.2 kilograms, hanging from 150 centimeter long string right here. Okay. The bullet embeds itself into the block, and the block then swings out a distance, an angle of 40 degrees right there. What was the speed of the bullet? There we go. Kind of a cool thing to do. This is how they used to know the speed of a bullet. Let me make a drawing of that, and then I will put some numbers, and then we'll use conservation of energy and momentum to solve this problem. Okay? All right. ballistic pendulum. Ballistic pendulum. All right, so what you have in here, you have something like this. Here's the ceiling. I'll make it one chord. Because I'm doing two chords here because I have the one I witnessed with our professor was two chords. But anyway, let's just make it the way the book looks. I have it drawn. Here's the ceiling. Here is the cable, and you got a piece of wood, a block of wood here. Okay, three-dimensional block of wood. Here's the bullet. You shoot the bullet with some unknown velocity. This is what we want to measure, V naught. Okay, I know the mass of the bullet. That's no biggie. It's 10 grams, he said. Okay, I can measure the mass of the bullet before I shoot it, right? And I also know the mass of the block. Got it? Okay, so the mass of the block, let me call it big M, is equal to 1.2 kilogram. Okay, so now I pull the trigger, I shoot the bullet. What's going to happen? Well, here is what's going to happen. The moment the bullet, I want to show you the picture of the moment the bullet is right there, about to enter it, right here. Here's the bullet. Okay, the moment the bullet enters the block. So what's going to happen? Both bullet block system are going to start moving with one common velocity, big V. Make sense? This is an example of inelastic collision, correct? Everybody pause and think about that. This is very important to know. The moment the bullet enters the block, okay, it's not yet embedded in there. Okay, it's right there. Okay, right at the moment it enters the block, both block and bullet are going to move with one common velocity. They're going to swing up like that. Okay. Now, eventually, they're going to swing up, and there is a latching mechanism. At least that's what when I was in the lab and how we did it. It's actually it stops at some point at some angle. I'm trying to do it here. So at some point here is the block. Here is the bullet embedded in there. Okay. And now, remember, it started at this height right here, and now it is at a new height right there, H, with an angle of, he gives it to us, he said it's 40 degrees. Okay, here, let me show you the picture. Here's the picture right there. Let me make it bigger. There we go. Look at that. So here we have, here is the length of the pendulum, 1.5, I didn't write it down, but anyway, here's the bullet. It goes to the block, it becomes embedded into it. This is the common velocity that I call big V. He calls it V1, I like big V. And then it rises up a height, some height H. It's not shown here. Okay? And now with this information, I want to find the speed of the bullet. Okay? Remember, H is not given to us. H is here. This one is not given to us, okay? All right, how do we do it? Here is how. I want to start with conservation of momentum between, I'm going to call this stage 1, stage 2, stage 3, okay? Just for the sake of explaining it to you. Look at stage 1 and 2, okay? As a matter, stage 1 includes the bullet here. This is stage 1, okay? The bullet is shooting from the rifle coming out. This is stage 1. You see what I'm saying? So stage 1 includes the block and the bullet before it hit the block. Okay. Stage 2, the bullet right there, the moment it enters the block, and now both are moving with common velocity, big V. Got it? Okay. So what is the momentum here? The conservation of momentum. Well, we have the mass of the bullet times the velocity of the bullet. And of course, there is no momentum for the block, so I'm just going to ignore it. Now, equals to, this is stage 1. Stage 2 is going to be this one. So that's the mass of the bullet plus the mass of the block, big M, okay, times big V. That's it. I'm just gonna box this one I'll come back to it in a minute. Remember, I have a lot of unknowns. I don't know V naught. That's what I'm looking for, and I don't know the common velocity of both of them. Okay. Next stage is this. I want to look at stage number 2 and 3 together using conservation of energy. Got it? Using conservation of energy. So here, well, what's going on? This kinetic energy that is happening here, the moment that both the block and the bullet are moving with one big common velocity, it's all kinetic energy equals to 1/2 m bullet plus m block v squared, big V squared. And now all of that, they stopped right here, stopped. All of it has been converted into potential. You know, this is the subject of our previous chapter. So that's equal to m bullet plus m block mgh. H is the height that has been gained here. Got it? Well, the masses cancel out, which is nice. Remember, I'm not interested in this big V. I'm interested in this V right here. So I need to eliminate it somehow. But before I do that, watch. 1/2 big V squared equals to GH. Well, what is H? H is the height. Remember, I actually showed it to you last video on how to find the height reached by the pendulum. And I'm not going to derive it again. Go back to the video and you will see that H is equal to L 1 minus cosine theta. I derived this formula for you. And I told you it's important. Where L is the length of the pendulum. Go back here, L. See what I'm saying? So I can plug that in back here. And therefore, I can say that V is equal to 2GL 1 minus cosine theta, all of that under the root. There we go. I got an expression for the velocity. Got it? Now I take that baby right here and I put it right there. And I find V naught. So let me do that. So starting from here, so I have mv naught equal to m plus big M times V, which is this one right here, one minus cosine theta, and then therefore the velocity V naught is m plus big M over M times 2GL 1 minus cosine theta. Let me eliminate that. There we go. To the 1/2. And there we go. I have this formula. Let me just change it to a different color just for clarity purposes. And then we have, there we go. That's the velocity. You see that, guys? Just plug it in. So if I want to get the velocity, just plug it in. I did it a little bit different from how he did it, but I think mine is clear enough, I hope. So the mass of the bullet is 10 gram, which is 0.01 gram. 0.01 kilogram, excuse me. 0.001, no, 0.01, that's right. And then the mass of the block is equal to 1.2, I'm copying from my notes, divided by 0.01. Okay, that's the first thing for the masses. 0.01, there we go. And then 2 times 9.8 times the length is 1.5 times 1 minus cosine 40 degrees, right? All of that under the root. You go through that, and I have gotten an answer of, did I get the answer? No, I did not, sorry. So let's assume that, I mean, you work it out. And his answer was, and I hope mine is correct, it's the same thing. He calls it V1XB, there it is. He got an answer of 320 meters per second. Please check my work and see if I get the same answer as his. This is his answer. His answer. So it should be the same as mine, right? I hope. Okay. There we go. Got it, guys? Okay. One more. And then I think you should be good, I hope. I want to do one homework problem. There are several homework problems, and some of them may be difficult. Like I said, you are welcome to ask me. Any problem that you get stuck on? Okay. The problem that I want to do is number 25. Let me show it to you in the book. I'm going to go to exercises. We are in chapter 11. So many questions. Let's go back to, okay. Number 25. There it is right here. Let me magnify it a little bit. There we go. This is the picture right here. You see that picture right there? Let me make it bigger. Oop, not this one. There we go. Okay. So it says, he said, a package of mass small m right there is released from rest at the warehouse loading dock and slides down 3-meter high frictionless chute to a waiting truck. The truck is down here, okay? All right. Unfortunately, the truck driver went on a break without having removed the previous package of mass 2m right there from the bottom of the chute, okay? A and B. A is easy. B is a little bit toughy for some of you. A, suppose the packages stick together. What is their common speed? He wants the big V. You see what I'm saying? That's easy, right? I hope. Okay, let's see how we do that. And then we'll do part B in a sec. Okay. So what I have in here, I'll go to my notes. Let me draw a picture of you for you. So I have something like this. The whole thing, the stupid eraser. Do it again. Here we go. And here is the mass, the block 2m. And then here is the block 1m. You see what I'm saying? And the height of the block is 3 meters. And then, of course, it goes, and it gains speed, and then it collides with that. So for case A, what happens here, let's look at the moment right there, what's going on here, okay? So what's going on, here it is, here's a picture for you. We'll call that block 2 and block 1. How about that? We'll worry about the masses later. Okay, so what happens is that block 2 and block 1 right there are stuck together, right? And they move with one common velocity, big V. Simple? Okay. So, however, this is AC. I want to draw for you BC, which basically when block 1 is right there, okay? So here's what's happening. Here is block 2, correct? Here is block 1. And it's moving with some velocity. We're going to call it V01. That V01 really is here. Well, how do I find that? How do I find this velocity? Well, we can use conservation of energy. He said block 1 started from rest, which means V here is 0, V0. Okay? And then it went down, and it's right at this moment here, assuming no friction here. This potential energy, mgh, which is 3 meters here of height, have been converted into kinetic energy. So this is what I want to do. So use conservation of energy. M1gh equals 1/2 m1 v01 squared. Make sense, guys? So the masses cancel out. So I end up with v01 is square root of 2gh. And that's equal to 9.8 times the height is 3. And that gives me, did I do the calculation? Yes, I did. I get 7.67. 7.67 meter per second. Okay? So in other words, the block 1, just before it hit block 2, right here, Okay, right here. It's an original right here. Its speed is 7.67, and I got that using the conservation of energy of the previous chapter. You got that? Now I can use, with those two pictures here and here, okay, with those two pictures, I can use conservation of momentum. Let's see. So with this one for BC, I'm going to be M1 V01. Of course, this one is 0 here, so I'm just going to ignore it. Equals to, now here I have M1 plus M2 big V. Well, what is M1? M1 is M, he said, and V01 equals M plus 2M. This is what he said, big V. Got it? So M times 7.67 equals to 3M big V. The M's cancel out, and therefore the common velocity is 7.67 over 3, and that gives me 2.56 meter per second. Got it, guys? Simple? Okay. Now we come to part B. Part B is a little toughy. Why? Watch. He said, oops, I'll go back to a problem. He says, suppose the collision between the packages is perfectly elastic. Is perfectly elastic. To what height does the package mass M rebound? So in other words, it's going to collide. Here, let me show you the picture. So for the second part, it's going to collide. Go back to the picture here. So it's going to collide here, and it's going to hit it. Probably package 2 is going to go this way, but package 1, because it's lighter, is going to collide and go backwards, and it's going to go up to some certain height here. He's asking for, what is this height? Got it? Okay, how do we do it? Well, again, I want to use conservation of momentum. I mean, you agree with me, this velocity still applies, right? I mean, the velocity of the block right before collision is equal to 7.67, whether it's elastic or inelastic. So this velocity is still applied. The only thing that is different is that here, if you look at the this part right here, we are assuming the collision is inelastic here. Okay, inelastic. So now we're going to assume that collision is elastic. So in this case, we cannot do that. We're going to need to use a different way. So again, please draw that diagram. I'm not going to come back to it, and I'll show you with that diagram in mind. We want to see how it works. So basically, here is the BC and AC. So here is BC, basically, which is very similar to the one we just did. So one, and of course this one is moving with V01, the one we have over there. And then here what happened is the different story. I have block 2 moving with this velocity, and block 1 is moving in the opposite velocity like that. This is V1 prime, and this is V2 prime. You got that? That's the difficulty. So that's AC. You understand that? I'm talking right there. What's going on right here? Okay? So you got V1 prime and V2 prime. Okay? Now, I don't care for V2 prime. I really care about V1 prime. This is what I want. Because if I know it, I can use conservation of energy in reverse, you know, momentum, equal potential, and then I can solve for the height, the new height. And that'll be easy. Okay? That's the plan. So I need to find V1 prime. Okay. How do we do it? Well, let's work out, looking at this picture right here, let's work out the momentum. BC, it is basically M1 V01 equals to AC now, minus M1 V1 prime plus M2 V2 prime. See that? Got it? Plug in the masses for now, because I have two unknowns here. I got V2 prime and V1 prime. Both of them are unknown to me. Let me plug the masses and just make it simplify it as much as I can. You know what I mean? So I'm going to have M V01 equals minus M V prime 1 plus 2M V2 prime. You see that? Masses cancel out, And I end up with this nice expression. Of course, V01 is 7.67. We did that already from part A, equal to minus V1 prime plus 2V2 prime. You see what I'm saying? So I have this expression right here. Okay, as you can see, it's a nice expression. However, I have two unknowns. I can't do it. I need a second equation to solve it. Okay, so what I do, since the collision is elastic, then the kinetic energy is conserved. Remember? So now I'm going to appeal to the kinetic energy, which basically the kinetic energy before equal to the kinetic energy after, right? So the kinetic energy before, look at this picture right here as we write the kinetic energy equation. So before, basically I have 1/2 m V01 squared equals to 1/2 m V1 prime squared plus, remember the minuses don't mean anything here because kinetic and squared, plus 1/2 m2, which is 2m, you agree with me on that? V2 prime squared. Okay? So halves cancel out, masses cancel out. So I left with V01 squared equals V1 prime squared plus 2V2 prime squared. Okay? And of course, V01 is equal to 7.67 right there. Okay? So it's squared. So I'm going to get that number. I didn't get that number. Sorry, I'm going to use a calculator. I did it differently in my notes, I guess. It doesn't look the same, but anyway. All right, so we have 7.67 squared. I'm going to get 58.8. So this becomes 58.8 equals V01 squared plus 2V2 prime squared. There we go. Okay, so I have this equation, this equation. Now I have two equations with two unknowns, this one and this one. But believe me, they don't look pretty. It's going to take you another page or page and a half of calculation to get that V1 prime and V2 prime. Why? Because they're squared. Okay, you can use method of substitution, that's fine, but it's going to take you a while. However, there is good news to this. Whenever you deal with elastic collision, this is the right way to go through it. What we have done is the official correct way of doing it. But there is a cheap way of doing that. Let me show you how. Go back to the book. I'm going to show it to you in the book. And that is, let me show you what equation. Write it down as I mention it here. They come in really handy. Equation, page 275. Let me go back there, and then I'll show it to you in the ebook. Let me find it first. There we go. Page 275. Let me just tell you here. Put it in writing. Equation 1129. Let me show it to you. It may take me a little while to fish it out. Chapter 11. What section is that? Section 3. Okay. Ballistic collision. Let me just take this one out. There it is, right here. Is that the one? Yep, this is the one right here. Do you see it, guys? Right there. Okay. These equations come in really handy. Basically, rather than working out this algebra between this equation right here, let me put a different color. This equation right here and this equation right here, which is a lot of algebra, I do urge you to work it out and see how long it is, how tedious it is. You know, please work it out. I have done it in the past. Or you can immediately go to this equation right there and use this. Let me write them down for you, and I will show you how useful they are. So they have said, you know what? I'm gonna write them down while it's kind of hard to swap between the two pages. I'm just gonna write it because I memorized them. So basically, V prime 1, okay, is equal to M1 minus M2 over M1 plus M2 times V naught 1. Okay, here it is. And V prime 2 is equal to, similar kind of, 2M1 over M1 plus M2 times V naught 1. There we go. Okay? Make sure you keep those handy when you're solving problems with elastic collision. How do we apply this to our case? Well, easy. Becomes really easy. Here is our picture, right? And by the way, they apply only if the second particle is not moving. Make sure you know that. I think, you know, I mean, it's your responsibility to read this chapter and know that. I can't tell you every little details here within an hour. So those equations apply only with ball here. Let me actually probably mention in the here. Perfectly elastic collision with ball 2 initially at rest. It works only for that. And okay, to be honest, most of the problem that we're going to deal with, the second ball is going to be at rest. The second object is going to be at rest. Okay, so we can just plug it in rather than going through this algebra. So let's do it. Let's do it for our case. So I want to find V naught 1 prime, remember? So that's going to be M minus 2M over M plus 2M, right? Times V naught 1, we already got it, 7 point something, 7.67 right there, right? .67, and then we work it out. So it becomes, the m's cancel out here, as you can see, and I end up with minus m over 3m. I didn't cancel it yet. And we will end up with negative 2.56. Excuse me. So we have V1 prime is equal to negative 2.56 meter per second. There we go. This is really what we are interested in. That's all. We're basically done with the problem. So basically, let me go back. So it says, go back to this picture here. So the ball collides with the block 2 with that speed. Okay, I mean, excuse me, it rebounds with this speed, the one I just told you. 2.56 in the minus direction, and then what happened to it, and then we can also calculate V prime 2, which we don't need, but we will calculate just for the sake of completeness. And then we want to calculate how far it's going to go up the height, up the ramp. You know what I mean? Okay. So now let me calculate V2 prime, which is 2m over 3m, V naught 1, which is 7.67. The m's cancel out, it becomes 2/3. And then when you calculate that, I don't have it in my notes here. Let's calculate that. So we have 2 divided by 3 times 7.67. Answer 5.11. So it's going to be 5.11 meter per second. And it's in positive direction, just gives it to us automatically. Okay, and then the last part, he said, what is the height? So the height reached, well, we just use conservation of energy, right? So here's a picture. So it goes like that, and then it goes up. So here is block 1 moving with velocity V1 prime right here. And it's going to go up. So it's going to, the block will stop here. And here is the height. So here's all kinetic energy, 1/2 mv1 prime squared, and here's all mgh. Equate them together. masses cancel out, and therefore the height is v prime squared 1 over 2g, and then you work it out. It becomes 2.56 squared with a minus, but it's not important, divided by 2 times 9.8, and therefore the height is equal to 0.33 meters, or height is 33 centimeter. Okay, got it, guys? Okay, you know, I've talked for almost 1 hour and 40 minutes. I think this is good enough. I am getting tired. Like I said, if you have a problem, if you have any issue with any of the homework problem, let me know, okay? And always make it a habit. Read the chapter before you look at the video. I mean, I don't talk about everything in the video, simply because I can't. It's just too much, just a lot of material. So read everything in the chapter. Try to do the examples, and at least scan through them. But read the chapter. And then I always suggest for you those lectures by Professor Lewin and Professor, forgot his name. Anyway, they'll give you a different perspective on things. They're not similar to the way I teach, but they are very, very good teachers. So they can be very helpful for you to understand this material. And then watch my lecture and then try the homework. Okay? Okay, that's it. Have a wonderful day, wonderful week. Bye-bye.